Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all our members to the group, and I also kindly request us to subscribe to our channel, ring that notification bell for various updates in sciences and mathematics, and also engage us in the comment section for more other discussions and similar discussion. Now, in this specific discussion, we're going to look at the concept of periods or a period, velocity, and acceleration. And in this case, we are going to also look at other aspects like a phase in some of our other subsequent videos. But particularly, I've chosen for us to do this one so that we can be able to tackle other preceding topics which we are going to encounter, especially under the concept of a one-dimensional simple harmonic motion. Now, I mentioned that this is going to be relevant for us in trying to understand various aspects of a motion, especially of elementary particles. And of course, in interpreting some of the aspects which we are going to come across in our day-to-day lives, like vibration of engines, the brain waves, and other related topics. Now, in this particular case, in our discussion today, I'm going to look at this specific aspect of velocity, periods, and of course, acceleration. And this is going to be in terms of a formula representation, which are going to be applicable in our subsequent discussions. Now, in our last discussion, I had mentioned that basically we can represent this aspect of motion in terms of an equation, whereby we had given the equation of motion of a simple harmonic oscillator in terms of this particular representation over kx m, the second differential with respect to t given as such. And of course, we are given this one is equivalent to 0 given as such, and this represented basically so this was a second differential, as we said, our equation for motion of a simple harmonic oscillator. Now, in this case, having discussed the concept of this specific motion, this basically is going to be a second differential equation, which is going to have two specific solutions, which of course we are going to consider for the cosine. In this case, I'm going to give it as a cosine of omega naught t plus phi. So this is going to be our representation for this specific, of course, equation of motion of this simple harmonic oscillator. And apart from this specific function of the cosine, I can give another one for x t is equivalent to a the sine of omega. This is going to be omega naught t phi. So I'm going to elaborate on these specific sections of the equation. But I presume that whenever we're going to talk about the concept of a wave function, we have actually done a discussion on that one. I'm going to put a link of that specific playlist in our description box. So kindly check them so that we can be at par with this one. So as I've said, it is going to represent the equation of a simple motion of a simple harmonic oscillator. And this specific equation is a second differential, it's a second order differential equation, which is going to give us two specific solutions. And this from these solutions, of course, these are going to represent the equations of motion of this specific oscillator. Now, in this case, we are going to have from our wave and anatomy, which we have discussed. These are going to represent the equation of motion of that specific types of cycles in terms of a wave. And therefore, we are going to have these specific representations for x. So this is going to be a displacement given in terms of x. And then we're going to have this specific element of t representing the time in seconds. So we can just give this one in terms of perhaps those specific representation. And then a represents what we refer to as the amplitude of that specific wave. And then we're going to have this specific representation for omega naught given as a frequency of oscillation. So this frequency of oscillation is going to be given in terms of radians per second. So this is going to be frequency of oscillation given in terms of radians per second given as that. And then we're going to have this specific element of phi, which is going to be a fixed phase. So in this case, these are going to be represented using these two specific equations of course, motion, which we have described for a wave. And whenever we're going to talk about the concept of a period, velocity, and acceleration, sometimes we're going to borrow from this specific representation. And as I had mentioned, the concept of a frequency, of course, we can see that this is going to be part of the element of this specific, of course, equation. Now, as I mentioned, of course, we're going to see that both representations for the sine and the cosine function are going to satisfy this specific concept of harmonic motion. But as we're going to see later, there are some of the aspects which we are going to note, especially for the cosine function, which whereby we're going to see that this is going to start from the initial position. The equation is going to satisfy a particular particle or under consideration that is going to assume this nature of motion from the initial position. But we're going to see that there's going to be a challenge, especially when we're going to consider the velocity component, whereby we expect that this specific velocity component is should of course be starting from a particular point whereby we are going to expect this velocity component is a discretion with respect to time. We're going to see that if we are going to consider that we expect the velocity component at this specific point of t is equivalent to 0 to be 0. But we're going to see that in this particular case, there's going to be a scenario whereby we're going to have this one, of course, or the velocity component with respect to time at this specific point not equivalent to 0 as such. And that's going to give us a challenge. But we're going to see that the equation of this specific concept of a cosine function is going to obey or be representing or satisfy this simple harmonic motion. Now, if we consider the concept of a sine function, which is also going to be a solution of this specific equation. Now, the sine function is going to be another possibility which we have said, which is going to provide a solution for us. But we're going to see that unlike the cosine function, for the sine function, this is going to be satisfying this specific equation of a simple harmonic motion. And of course, we're going to see that the object is going to be having its starting point noted as the initial equilibrium position. So the equilibrium position is going to be its initial point, but it's going to satisfy, of course, this specific component of the velocity, whereby we're going to see that it's going to be, and perhaps we're going to look at those ones in details in some of the discussions of waves and mechanics. Now, in this case, I'm going to leave that one there, and we're going to look at how we can represent this specific aspect using the previous discussion we had of course, on the concept of an anatomy of a wave, and that's going to open for us a window of understanding these two specific representation for the solutions of this, of course, particular equation for the simple harmonic oscillator, which have given as such. So in this case, we are going to see that the concept of a period can be described in terms of the time taken for one specific cycle, and this can be given in terms of perhaps I'm going to do away with this. So the period basically is going to be given as the time it takes for an oscillator to go through one complete cycle, and we can give it as so let's have as the period implies the time. So the period represent, you can just give it this one, represent the time taken for one complete cycle. So perhaps I can give it in a statement form as such, but particularly it represents at the time it takes for an oscillator to go through one complete cycle. And this is going to be given, so period can be given in terms of t. So whenever we're going to represent that one, we're going to represent period. So in this case, this is going to be differentiated. Whenever we're going to use it, we're going to differentiate it from the previous aspect that we have learned on the concept of kinetic motion. By trying to mention it given as such. So this can be represented as the reciprocal of frequency given as such. So we can have our equation given in terms of the period is equivalent to 1 over f given as such. So frequency, we say these are the number of cycles that are going to be given per a second. Now in this case, this is equivalent to, so we can give this one in terms, remember from our previous discussion, we had defined the frequency in terms of pi and of course omega. So therefore this is going to be given in terms of 2 pi over omega given as such. And this is going to imply the concept of what we refer to as period. Now, as I had mentioned, of course, this is going to represent angular frequency. So this is going to represent angular frequency, but we're going to differentiate it from Remember when we were talking about the concept of circular motion, we had given this specific displacement, angular displacement with respect to time as omega. Now in this case, to differentiate it from angular this aspect of speed, we are going to have this one given in terms of course, omega naught given as such. And that is going to be differentiating our discussion of the concept of angular frequency from this specific representation for d omega over dt from circular motion, which basically is the same as angular speed given in terms of that specific equation. So therefore, this is going to represent our period, which is 2 pi over omega naught, given as such. Now, the velocity and acceleration component, which we are going to look at from the simple harmonic motion, can as well be described. So we have decided that if we have an equation which is going to be, of course, with respect to time, given as a the cosine of omega naught t. So in this case, we can, of course, identify the concept of what we refer to as a velocity from this specific component. So we have decided that basically velocity is the first derivative of displacement, which we can give in terms of dx over dt. So therefore, we are going to find a derivative of this x with respect to time in order for us to find the concept of this aspect of velocity. So or therefore we can find the first derivative of this one. So if it's with respect to time, if we had this specific component perhaps given in terms of if we just assume the aspect of time, we're going to have this one given as x, and therefore we are going to find d over dx of this specific element, and this is going to give us the aspect of this specific representation of so let me just have it as that. Perhaps I can just reserve it like that to avoid the confusion. So we're going to have this one as a derivative with respect to time given as such, and then we shall just have to conserve our specific representation for this one. So we're going to have this one as a dx over dt, so implying dx over dt. So we're going to differentiate our component over x, and this is going to give us a representation of d over dt over this specific aspect over a, the cosine of omega naught t, and this is going to give us negative omega a. So this is going to be a derivative of the trigonometric functions which we have done in some of our videos in mathematics. So we're going to have this one given in terms of the sine over omega t. So this is going to be omega naught t given as such. So this basically is going to represent a velocity, since it's going to be the first derivative over x given as such, and therefore it's going to be representing our velocity component. So this is going to be our second aspect from the period which we are going to determine. And as we said, we can as well represent acceleration in terms of this specific aspect of the simple harmonic or the simple harmonic oscillator, whereby we're going to have acceleration basically given in terms of the second derivative of this specific element of x. So we can give this one. So this was our first derivative which we had analyzed in order for us to find velocity. So the second component of the second derivative of this one is going to be giving us dx over dt, the square of that one. And this is going to be, of course, the differentiation of this specific component with respect to time, and this is going to be a second derivative. So therefore, we are going to differentiate this one twice, whereby the first differentiation gives us omega. So this is going to be omega naught a, the sine of omega naught t. And the second, of course, a derivative still is going to be giving us the derivative of the sine is equivalent to, of course, the what we refer to as the cosine. And therefore, we are going to have this one in terms of a negative omega naught squared. And of course, this is going to be this specific element. And then we are going to have the cosine of omega naught t given as such. And that is going to represent our, of course, acceleration given as such. So, but if we try to consider from this one, we have given this specific aspect of the equation. Remember our representation for the component of x given as that one. So therefore, this is basically going to be representing our x. So therefore, we can give our acceleration in terms of this given in terms of a negative omega naught squared, and then we're going to have our x given as such, and that's going to form a part of the representation of acceleration, considering these specific elements which we have discussed in our from our previous example. So that is it for now, guys. Kindly check our description boxes for various links of other videos, and also ring that notification bell to be getting updates on our various discussion we do in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.